Okay, so it looks like last time we got our force diagram drawn. Again, the tension parallel to the string from the point of contact. And hopefully we talked about that hanging mass. It has its own tension, but overall it's a downward force at that point equal to the weight of that added mass. Okay, so remember the problem on the previous page, we did not have an added mass. And then we have the beam itself, so center of mass, drew the force diagram, gravitational force. And then that pivot, don't get in the habit of assuming it's only vertical or only horizontal. It's usually a combination of both. So it's an angled force. Good deal? All right, and so determine the tension force that the horizontal cable exerts on the 20-kilogram beam. And so we want to put our fulcrum here because they don't tell us where to put the fulcrum. Again, sometimes there's strategy. What might be a good place to put our fulcrum? Somewhere. Be more specific. So one strategy is, well, let's put it at an unknown force. Now we're trying to solve for tension, so maybe we don't start with the tension location, and we know the two weights. Do we know the pivot force? No, so let's put it at the pivot. And by the way, your drawbridge, hanging sign type of examples, I think 99% of the problems I've seen, your hinge is always at the wall. But in the big scheme of things, it doesn't have to be. And so with this now defined, we should be able to get our lever arms. And so hopefully you can tell that the pivot going through the hinge will have no lever arm. And so it'll have no torque. What about the weight? Does the weight have a torque? Does it have a lever arm? Yes. And so it's going to be down on the right. So it's going to wrap around clockwise. Okay. And then we got to identify the lever arm. Watch me draw. Is this the lever arm from the fulcrum to the center of mass? Is this the lever arm? No, we want our force to be perpendicular. True story. You could do all the geometry with the forces, or you can do the geometry with the distances, okay? You got to do it somewhere along the way. Me, I look at this picture and I'm like, all the forces are horizontal and vertical. I'm going to leave them alone. So I'm going to choose to do the components of the distances. So which component is perpendicular to that gravitational force? Well, first, let me draw it in. Wouldn't you say that this is a perpendicular distance? Hopefully you see a right triangle. Hopefully you see the hypotenuse. And if it's drawn from one edge to the center of mass, then the hypotenuse is equal to what value? 0.5 meters. And so my 0.5, and our picture is going to get a little cluttered. So my future drawings, I'll try to draw separate. Okay. But that's going to be 0.5 meters. I need an angle somewhere. Well, if we think about that purple tension horizontal axis, and then the horizontal lever arm I have, isn't that 15 degrees that they identify? This bottom left, alternate interior angles or such. And so with that, we know the hypotenuse. What we're looking for is adjacent. And so what are we going to use to find the lever arm for gravity? Cosine. And you're like, but Ms. Earhart, the equation on the formula chart says sine. A lot of times you will use sine, but there is the occasion. And by the way, you're not going to be flat out told when to and when not to, right? So drawing them out should help you decide which function. And so R per G, the component, is equal to that 0.5 hypotenuse times cosine 15 degrees. Grab a calculator, make sure you're in degree mode, and let me know what you get for this component. And we got some decimals here, so don't tell me it rounds to 0.5. The hypotenuse is 0.5. Give me 2 or 3 digits, not 5. That's fine, that's fine. 0.482, 3 non-zero digits. There you go. Good deal on that one? Everybody know what we did and why we did it? Okay. Let's do the same thing for each of the other 2 forces. So the blue added mass, well, it's down on the right. It's going to have clockwise. It's a vertical force. So I want to look for a horizontal distance that's perpendicular. Do you notice? Now, here's where I'm going to draw separate. Do you notice that from the fulcrum to the edge of the beam where it's located, the force is located, that's a full meter. And we just saw alternate interior. And so if that's still 15 degrees, the horizontal component of this lever beam triangle is going to be our lever arm for the added mass. Again, it's adjacent, 1 meter's hypotenuse. So same story, the lever arm is going to be the hypotenuse 1 meter times cosine 15. And don't tell me it rounds to 1. Give me 3 decimals. 0.96 what? 4 meters. Everybody good there? And I think we can squeeze the purple on our picture because it's above the beam. So that one's not too cluttered just yet. But notice it's a horizontal tension. So I need a vertical lever arm. So we can extend the line of force and go from the hinge fulcrum to the line of force. Again, we want a horizontal lever arm. So the lever arm for the tension is opposite 15. Now notice where it's connected. The hypotenuse, maybe I will redraw it. The hypotenuse for this tension lever arm distance is going to be what? Where it's connected? Hypotenuse is 0.7 meters. We want the lever arm opposite 15. Now what trig function do we use? Sine. And so our perp for tension is going to be the hypotenuse 0.7. This time it is sine 15. Okay. And 3 decimals. Let me know what you get. 0.18 is fine. Meters. Okay. We have 3 forces, 3 torques. We have 3 lever arms. Now we need to, well, it is an equilibrium. Do they mention the string being cut? Do they mention any words that would imply it's not an equilibrium? No. And so we'll assume it's equilibrium. Oh, and tension is going to wrap around the fulcrum in the counterclockwise. And so whichever way is positive, whichever way is negative, with equilibrium, we can say that the clockwise torque balances the counter. And so let's find some room here. I'm going to simplify that. And so down below, torque clockwise equals torque counterclockwise. And so the torque due to tension is going to balance the torque of gravity and the torque of the added mass. Each one has a force and lever arm. Now we should have enough. So the tension is the force we're looking for. And we know the lever arm for tension. And so we can plug numbers as we go. That was the 0.18. Torque of gravity is the force of gravity, also mg, times its lever arm. Mass, they told us, of the beam was 20, times gravity 10, and its lever arm was that 0.482. plus the added mass. Be careful here. I've been calling it an added mass. Did they give us kilograms? They said it's 420 newtons. Am I going to multiply newtons by gravity? It's already got it in there. It's already in newtons. So I'm just going to keep the 420 and its lever arm 0.964. And so I don't remember our answers. So someone quick on the keyboard, let me know what you get. It's a big number. It's a big number here. 700 and what? 90? 85? Seven, six? Oh gosh, we're all over the, it's probably rounding of the lever arms, right? So some people might have used 2 places, some people might have used 10 places. And so, yes. Hold on, question? 0.482 was our gravitational lever arm, and that's in red. So we did the center of mass, that hypotenuse was 0.5, and alternate interior, we figured out the 15 was in the bottom left of that red triangle. And the horizontal component is the one that's perpendicular to my FG. So that's the lever arm. It's the cosine function. Yeah, right here, I'll highlight right there. It's perpendicular to the actual force. That's what you use to do torque. You want the distance, whatever it is, whatever component it is, to be perpendicular to your force. Okay. Okay, so did we decide on the end? I've heard 67, I've heard 90, 85. 785. Did you use my numbers?
Yes.
Okay. Ish. Y'all textbooks are probably around that to probably, 2,800 or 2,780. Okay. And so in the spirit, hopefully you get around here. Good deal? So not much different, a little more trig, but pretty similar, right? Okay, that's going to be, I think, our last equilibrium example today. Again, there's the tip or slip that is the last moment of equilibrium. And by the way, those are on pages 9 and 10. So if you want to just go to 9 and 10 real quick, you can put a little, maybe it's on the May exam, but we decided not to test it just due to timing. If we had an extra day or half a day, maybe. So that bottom of page 9 is a tip or slip. It's an equilibrium application. And then also on page 10, maybe it's on the May exam. This one though gives you some numbers and says, okay, does it tip? Does it slip? Or does it both? And again, that slipping is your linear motion. You have to figure out, is it in linear equilibrium or not? And then that tipping, are you going to have equilibrium with torque or not? So give it a try. It's an extension of equilibrium. And so back to page 8, we'll do a little bit of this one, and then there's a similar one on the next page. We've got a beam. It's on a wall with a hinge, so it feels the same, but no string. By the way, AP, if they give you a string like the top one that we just did, they love to cut strings. So maybe it's similar to this after the string is cut. It says a uniform rod of mass M and length L can pivot freely. We're going to ignore any friction. True story. Isn't that rubbing, rotation at the hinge probably in real life going to have friction? Yeah, but we'll ignore that. About a hinge attached to the wall is pictured. So I'm going to draw my triangle there. Again, I like triangles for my fulcrum hinge. The rod is initially held at rest and then released. Do you think the rod's just going to stay there in the horizontal alignment? No, the rod's going to rotate down, right? And so it's going to rotate clockwise. At the moment of release, not 5 seconds later when it crashes into the wall, But the second we release it, two things. What's the angular acceleration and what's the linear acceleration? So we'll get to see that non-slip application in part B. And so angular acceleration happens because of a net torque. And so here's what we're going to do now. Always start force diagram. They've got the gravitational force from the center of mass. Check. What other forces are at work here? Well, initially someone's holding it, but we're going to look at it just after they let go. So there's no tension, no applied force, but there is a hinge force, right? And I told you assume that they do have an angle. But since it's at the pivot or hinge, no torque, no lever arm. And so the only thing to have torque is based on the weight of the rod, yes? And so one torque, one direction, we're not in equilibrium at all. And so I'm going to say net torque equals the torque of gravity. Hopefully this feels similar to what we did with forces. F net equals the sum of the forces. We're summing the torques. Well, let's take a closer look at Newton's second law. We did this day one. F net equals ma. Net torque equals I alpha. Alpha is the angular acceleration that we're looking for. What's I? And so I'm going to use this page. Come over to the side. Paper people, I don't know. Get a piece of paper, find a blank space, go back to page 1. I don't know. Let's do a little bit of inertia talk. So previously, I put my arms out, I pulled my arms in. I said, I'm not changing my mass, but I'm changing how the mass is distributed, okay? And so rotational inertia, which is also called moment of inertia in some textbooks. I think your textbook does rotational, and that's the way it's labeled on the formula chart. It's a variable I. It does not equal m. Here's the equation in generic form. Now, I'm not even going to send you to the formula chart. I'm going to go in and tell you it's not on the formula chart. But please, you don't have to memorize. You don't have to memorize it. And so even though it's not necessarily given in textbook problems, because they say you have a textbook, we gave you a chart, go look it up. AP questions will give you this equation, okay? Now you may be wondering what the K is. You're like, spring constant, what? So K, for whatever reason, it's just representing the constant. Here we're gonna call it the shape constant. Remember I said inertia is how the mass is distributed. And so I've got a little box of objects. Sorry, video people. I am holding in one hand a ring, or also called a hoop. It's hollow. And so all the mass is where? On the inner or the outer? It's around the outer perimeter, right? In my other hand, I have what's like a mini bowling ball, and it's heavy, right? It's full, it's not hollow. You could have a basketball hollow sphere. This is a solid sphere. Where's most of the mass located? If we think about a sphere as many different sized rings, where's most of the mass on a sphere? It's towards the center, right? At smaller radii. This one, all the mass is in the outer. Here, most of the mass is closer to the center. Think about me spinning my arms. Out, I move slow, hard to rotate. I bring my arms in, closer to the center axis of rotation. It was easier to spin. I went faster, yes? And that's kind of the name of the game with inertia. It is mass, it is their radius, but really it's how the mass is distributed. And so one of the more important parts of this equation is that K. Now you don't have to memorize these fractions that I'm about to show you, okay? And please, no judgment on my artwork. I never claimed to be an artist. here we go. Here's the common ones. There's like 4 common ones. You got your ring, also called a hoop. And so it's just like a hula hoop. It's a ring. So there's a 2-dimension ring. The K value is 1. And so the inertia would just be 1 mr squared. By the way, it's also 1 for just a person standing on a beam or something. That's coming. Point masses are also 1. If you want to draw a point, go for it. Well, the other one I showed you was a sphere. So a solid sphere, like a bowling ball, not a basketball, is still circular. And I'm just going to color this one. Okay. By the way, your textbook, your online textbook, I know you're reading chapter whatever, right? I know you'll find the chart with 3-dimensional computer pictures drawn, right? So, or you can Google for it. It's a very common type chart. But your solid sphere is 2/5. What? Do we have to memorize all this? No, you do not. AP may not flat out tell you the shape constant, but they'll say, oh, for this problem, the inertia of your object is 2/5 mr squared. And then another common is a solid cylinder or disc. So we've got a solid cylinder, and I'm holding it up. I don't really know. It looks like a hockey puck, a thick hockey puck, okay? Or it's also called a disc. Now this one, bear with me. I'm going to try to go 3-dimensional. Can you buy it well enough? So this is, just think hockey puck. That's like a bowling ball. And so your solid cylinder is real common because we love the fraction 1/2, right? It's so user-friendly sometimes. That one you'll probably see the most often. And when I say we, I don't mean me. I don't mean Alan, it's just the world of physics. There's a lot of solid cylinders. And so the inertia would just be stated as 1/2 mr squared. Another one is, I got a meter stick. It's a stick, right? It's a rectangular stick. We'll lump it in as a rod, okay? Now this one actually has 2. And so I have this meter stick. I can hold it at 50 centimeters and I can rotate. See this? Rotation. Or I can do it above my head, either way. I'm rotating 50 centimeters on one side, 50 centimeters on the other side, yes? Or I can hold that same exact object at a different location, an end. So I've got my hand at the 0 centimeter mark. Can't I still rotate it? Okay. What do you notice? This circle that I'm making here, although it may not be a complete circle, look at the top portion, compared to, what's one thing you notice? I hope you notice. The end of the stick, when I hold it at the other end, doesn't it make a full 100 centimeter radius when I hold it at one end? The radius of the circle it's making is 100 centimeters. But if I hold it here in the middle and rotate, it's got a diameter of 100, but now a radius of 50. So your radius changes based on where you hold it, and also the shape constant changes. So let me write it up here for both scenarios, and then I've got a barbell demo for you to feel inertia, because I can spin things up here all day. You can't see forces really, but you can feel forces, okay? And so the rod has 2 scenarios, and so we can spin it, or I can put the fulcrum at the center point, and it has a K value, 1/12. We probably won't see that often, but it's there. And by the way, where'd these fractions come from? calculus. So we don't get into the calculus in here, but if you're curious, next year, if and when you take AP Physics C, either course, the combo or the mechanics only, is going to go over the calculus of these shape constants, okay? You break every little section of each object into little bitty divisions, right? And then you add it all up, okay? Or maybe we rotate the rod about one end. And so for this one, it would be 1/3. That one you'll probably see more often. Okay. And so now let me get my barbells and do a little demonstration. And then I'll pass them around. Hopefully I can trust you. These are not swords. These are not weapons. And when you start rotating them, please don't hit your buddy next to you, okay? And don't drop them because they, they're not literal barbells, by the way. They're homemade barbells. I took a rod, a demonstration rod, and I duct taped some masses on there, okay? Well, so I have a rod and I can hold it in a couple places. I did add some point masses, okay? So this is really like a system. And so here, this first one, I've got the 2 masses, which are each 500 grams. So it's uniform, it's balanced, left, right. I'm holding it in the center-ish, right? So I can rotate and I feel something, okay? Now, if you want, take that same one, move your hand, don't necessarily mess up my masses, and try to rotate this one. It's more of a workout. It's more of a challenge, okay? When you hold it in a different spot. But then I also have another rod. What did I do with the 2 added masses, which, by the way, identical masses? I taped them where? Closer to the center, okay? There's your 2 comparisons. And so when they're closer to the center, do you think it's going to be harder or easier to rotate? Easier, because where's the mass? Closer to the center, okay? And so you can do a couple of rotations. You can do the comparison, where the mass is located, and then try and hold one of them offset, okay? And do that rotation. So you feel the force, you feel the inertia, you feel the difference. Good deal? Okay, so it's just going to take a little time if you want. So I only have these 2, so I'll pass them around. Please, safety first. Don't whack your friends, okay? Especially you. What? Okay, let's start over here. So give it a try and then pass it on to another table. Pass them together. Don't let the 2 separate, okay? And somewhere I have, oh, well, it's a different length. I do have a rod without mass attached, but it's a different length. So technically that's different. All right, I am going to keep going. All right, so stay on task. Stay on task. Here we go. So last reminder, don't memorize the equation. Don't memorize the constant values. You'll be given those, I promise, okay? Promise, promise. And so we come back to this rod. It's going to angularly accelerate due to the torque of gravity. Let's actually solve for alpha. And so let's get our torque broken down into the force, mg. And we already got the lever arm. Oh, they gave it to us. So if you look back in the picture, they have mg identified from the center of mass. And then the distance between the fulcrum and the force of gravity is what? Horizontal distance, L over 2. And so that's going to be our lever arm. Okay. The last thing in this equation, I need to plug in our inertia. So this is a rod attached at the end, at the hinge. So this is that 1/3 ml squared, which, by the way, I just now remembered with rods, they usually write it in terms of length. So I'm going to make that change because the constant is determined by the full length of the rod. So I'm just changing those 2 equations, 112 ml squared and 1/3 ml squared. And so our hinge this beam is at one end, we'll use the 1/3 ml squared. Okay, next step. 1/3 ml squared times alpha equals mgl over 2. What do we notice? What do we notice? Cancel mass. Anything else? A set of lengths. So L squared on the left, square goes away, and then the L in the numerator on the right cancels out. And so we're solving for alpha. And so we want to multiply both sides by 3. So our fraction can be written as 3/2. And then I have G in the numerator, and I got to divide by L. If you just want to write it as 3G over 2L, that's alpha. This is a variable problem. They didn't actually give us values. Now you may be thinking, oh, G, I know it's 10, 9.8. Can I go on and multiply that out? I'm sure you would still get full points because y'all on free response, make sure you show the work leading up to the answer. Answers alone get you nothing. You got to show the physics first, okay? But typically on variable solve, you keep it in terms of G, okay? All right, B, it'll go quicker. What is the linear acceleration of just the tip of the rod, not the hinge, the far edge? And so I'm going to go back to the picture. Every little point on the rod, and I'm just going to pick some, okay? I'm going to kind of think about 4. Each point is going to rotate down, yes? Each point is going to sweep the same circle, if you will, in the same amount of time. And so each point has the same alpha. That's the first concept. Same alpha. So all points, same alpha. But linearly speaking, each of those points has a different distance from the hinge. They have a different radius of the circle they make, right? And so the acceleration linearly is going to be different. So they have different linear acceleration. Hopefully you remember which point here on this beam, the one closest or the one furthest, is going to have the greatest linear acceleration. We might have actually talked about it with linear velocity, but we see the same relationship here with linear acceleration. The bigger the radius, the bigger the linear acceleration. And so if I want to draw some tangent linear acceleration, and I'm just saying A1, A2, because 0.1, 0.2, these are not forces. And it's tangent to the circle they make, okay? And so we're not going to do linear pieces for every point. They just want the very, very end. And so knowing it has a big radius, a big linear acceleration, y'all remember the non-slip equation? It was some linear quantity equals the angular quantity times radius. We've written it out for, I think, the distance when we compared one full circle, okay, compared to linear motion, and same with velocity. So these non-slip equations, hopefully you use them so often, they become habit, they become second nature. And so, again, alpha is the same at all points. And they tell us, this is all variables, so it's already solved for linear. So we know alpha is that 3G over 2L. And then times, what's that radius? What's that distance to the end of this rod? L. So basically what happens here? L cancels and we're left with a linear acceleration of 2/2 times G. Again, variable problems, you usually keep it in terms of G. And that would be your answer here. Okay. Questions? Elias, look to your left. Where's the other rod? Oh, okay, okay. Okay, this last one, it actually does take a little bit longer if you variable form, okay? I know we got to get through some more problems. And so I'm going to say try this one, but please know that for the person that's going to stand on the beam, alpha of the person is going to be the same as alpha of the rod, okay? And so that's how you would get this one started. We're going to do this with math on the next page, okay? So just to save a few minutes here and there, it adds up. I'm going to have you try this one. So on page 9, we got a person standing on a rod, a beam, okay? It's connected with a string, a cable of some kind. What is the inertia of the system? When y'all are done, just put them on the side over there. Okay. And so inertia of the system, the person has mass, the person has inertia, and the rod has it. So I system, oh, okay. Sorry, I thought y'all had already got it. I rod plus I person. Each one has that kmr squared. So the shape constants are given here. And just a reminder, inertia is that K shape constant times mass times this radius or length squared, okay? And so for the rod, notice where's our fulcrum? They don't specify, but where probably is the fulcrum? Let's draw in our triangle. Probably at the wall, the hinge, the pivot. So I'm going to put it right there. Force diagram, quickly. We've got FG of the rod. The person has a gravitational force. The pivot has some kind of angled force. Hopefully now we've bought in that it's probably going to be angled. Now, since it goes through the fulcrum, the pivot has no torque. And then there is a string. They're going to cut the string in part 2, but for right now it stays intact. So tension parallel to the string. Everyone good there? So part 1 is just about the inertia. It's not about the torque. And so the rod is going to be that 1/3 ml squared. And I can plug my numbers in as we go. The mass of the rod is 100. The length is a full 5 meters. Don't forget to square. Full. Say again. It tells you. Yeah, we're on the next page now. There we go. And then for the person, they tell you it's 1. This is like that point mass, okay? Don't hit. Just set them over there if you don't mind. And so 1 mr squared. Now this is weird. Watch. Yeah, that's fine. Just on the table as a whole. There you go. Okay. So the person's not a circle like these objects I've been showing you. How can the person have a radius? And we're not going to do something weird like sometimes physics does and assume the person is a sphere, okay? But it's the radius that it's going to make with the fulcrum. And so if you think about later, when we cut the string, that person, as long as they stay in contact with the beam, they'll rotate with a constant radius. Come on, y'all, come back, come back. And so the radius of the person is going to be that 1 meter given from the wall. And so 1 times 50 times that 1 meter squared. All right, let me know what you get. Inertia of the system. Go quick. Y'all are going to make me record another video. It's not hard, but you know, sometimes I forget to just hit the button. And that's why I don't get it recorded. but no tech issues, knock on meter stick. 8, that sounds good. 883.33. Oh, what's the unit for inertia? Miss Earhart, you haven't taught us the unit yet. It doesn't have a nice Newton or joule or watt. It really comes from the equation. And so the unit, well, the constant has no unit. Mass, it's kilogram. Times a radius squared, SI unit for radius squared would be meters squared. So it's 883 kilogram meters squared. Don't say per. I know, it's crazy, I know. It doesn't simplify. Why simplify some and not the others? Well, I don't have a famous last name like Newton, right? Or Joule, Mr. Joule, Hertz, I don't know. Yeah, so we'll claim this one as an Earhart. I'm gonna call EH, there we go. Nah. But that is our answer, 883.33. You know, AP exam, you could round that to 883, 3 non-zero digits. Part 2, now the string is cut. AP loves to cut strings. Watch out. I know, they'll be okay, it's physics land. There's nice marshmallow cookie, something down below. The person will be okay, no one gets hurt, okay? I'm sure. What is the initial? Why would they say initial? Well, y'all, if this person and beam fell long enough, probably the person would lose contact with the beam, right? They would fall independent. And we don't want to look at it 5 seconds later when it smacks the wall that it's connected to. And so it's just cut, pause. What's the initial angular acceleration of the system? And then it says, what's the initial linear acceleration for both objects? Now, I know some physics problems will say, oh, we want rod and person, and then you do it and you get the same answer. They are different on this one. So there's 3 different answers that we're going to solve for here. Stay with me, this is the new stuff. And so rope is cut. Who or what force is going to have torque after the rope is cut? What force has torque after the string is cut? The 2 masses, right? Pivot still doesn't have torque. Tension's gone, like literally 0 is a force when you cut it. And so it's just the 2 gravitational forces, and thankfully they're in the same direction. Can we just call it positive? It's the standard negative direction, but they're both going to go forward. So here's where I'm going to change and just say positive direction. And so let's do the 2 torques. So net torque equals the torque of the person plus the torque of the rod, plus same direction. Then we can plug in Newton's second law of rotation. Net torque equals I alpha. So there's the Newton's second law piece. The torque of each is going to be their mg gravitational force times the lever arm. I got to go back up to the picture. We didn't talk about the lever arm of the people yet, or the masses. It tells us the person is 1 meter from the wall. And if the fulcrum's on the wall, then this horizontal distance is going to be a lever arm of 1 meter. What would the lever arm, while I'm here, be for that gravitational force of the rod? It's a vertical force. So from the fulcrum to that vertical force, it'd be 2.5. Beware, the inertia of the rod depends on the full length, but the lever arm of the gravitational force, your lever arm for the rod is 2.5. They are different distances. Okay, let's go plug our numbers in, or the rest of the variables, I guess. And its lever arm plus the mass of the rod times gravity, and its lever arm. And they told us that the person is 50 kilograms times 10. Lever arm was 1. Mass of the rod, they said, is 100 kilograms times gravity, but its lever arm is 2.5. Now just do different color because that's where a lot of students will make the mistake. What about I alpha? Well, I, it's for the system. So that's why they asked us part 1. If we hadn't done part 1, we'd have to find the inertia of the system. And so that's that 883.33. I believe someone can calculate and tell me I'm wrong. It's okay, but I think last period we got 3.6. Someone calculate, let me know. What would the unit be for angular acceleration? It's not linear yet. Say again.
Radians per second squared.
Radians per second squared is correct. Okay, and this is for both of the objects. It's the same. But now they ask, what's the linear acceleration? And so for linear acceleration, this is where we want to use that non-slip equation. Okay, assuming the person doesn't slide off the bridge as soon as it's cut. Eventually, maybe 5 seconds later, maybe. But here, when they rotate together, then the linear acceleration is equal to the angular acceleration times radius. So they'll have the same alpha, but their forces, their center of masses, are at different radii. And so for the person, it'd be 3.6 radians per second squared times 1 meter. Well, numerically, it's 3.6. What's our SI unit for linear acceleration? What's a radian per second squared times a meter? Just meters per second squared. And so this is where radians isn't really a physics unit. It's a placeholder to use as needed. It's not needed anymore. It just goes away. Okay. All right. What about for the rod? Same equation, alpha 3.6 radians per second squared, but this time, what distance are we going to use? So do we use the full length or do we use the center of mass distance? The center of mass. And so here we want to use that 2.5. Maybe I make it a different color to prove a point. And then calculate this out. And I think it comes out a very nice, 8.5. And then it would again be meters per second squared. So they have the same angular acceleration as long as they rotate together, but they have different linear accelerations, okay? If the person moved out further, and it was the same story, they would have a greater acceleration, right? Questions on that? Okay, at least one more. I think I can do it with time. Reminder, bottom of page 9 and page 10, that's that tip or slip. We're not going to ask you a test question about it, but at some point, hopefully you think about, you try it before the May exam, okay? And so try those another time. Page 11 is going to be, I'm going to use one of those as our bell ringer next time. I want to get a pulley started. Next class, we'll finish up pulleys and then start rolling our objects down a ramp or a horizontal surface, okay? But pulleys in the fall, we ignored the pulley disc itself. We could have cared less if it rotated or not. We just let the string slip over as a pivot point, yes? Y'all remember it just changed the direction of motion. So down on the right was up on the left. Well, all that's still true, except now the disc is not going to be frictionless. It's not going to be massless. In other words, if our disc that's connected to the pulley there in the center, if it has mass, and technically it needs grip so that the string will rotate it, so it'll turn it, yes? Not just slip. And so if you have friction and mass, you're going to have rotation. It's going to take energy to rotate that disc. The more inertia it has, maybe it's a different shape. Maybe it's bigger, literally with radius and mass. It's going to be harder or easier to rotate. And so in the fall, it says at the top, if rotational inertia of the pulley is ignored, what's the acceleration of the system? Now, again, timing, I'm going to go a little quick on the old stuff. Okay, we basically ignore the disc, the pulley disc. And so the only forces, and by the way, this one's set up so that M1 is bigger than M2. And so we've got our big M1G gravitational force. M2, I'm going to draw it like a fourth of the size. You'll see why in a second. Well, there's another force exerted on each one. There's a string, so we have a tension force pulling up on both. Okay, so think last fall we had tension. And so I'm going to draw where it exerts. And so there's a, half the size-ish, a tension up. And if you remember Newton's third law, these two tensions are going to be equal in magnitude, opposite in direction. You remember that? Now, technically, the string is touching the pulley, but in the old fall, our pulley was massless and frictionless. So it was just a pivot point. And so we can totally ignore the disc. And so we had some FNet statements. Again, I'm going to go a little quick. So for the first one, Newton's second law, FNet equals MA with a couple ones equals that M2G minus tension. Minus because tension pulls up. Shouldn't it be positive, Miss Earhart? Well, if M1's bigger, what's its forward direction? M1 will go down, right? M2 will go what direction? Forward. Up. And that's not a mistake. Up on one side, down on the other is the forward direction for each. Now we can write a FNet statement for the second block. FNet 2 equals M2A. And then that one has a positive tension and a negative weight. And at that point, we can add the two equations together to make our system equation. And now, why did I not put a subscript on the acceleration in each statement? How come not A1, A2? Do you remember? You release them both from rest. They're connected. They're going to have the same speed up or slow down. They're going to have the same acceleration. And so we can add the masses times that same acceleration. And we've got Newton's third law, tension positive, tension negative, equal in magnitude, opposite in direction. As a system, it's going to cancel out. And so we're left with, uh-oh, I got it wrong. Y'all didn't tell me my subscripts were backwards. Got to make that change. And so this one. And if you want, gravity is the same for both. You could factor out G, but in the end, your acceleration is the difference in the weights divided by the sum of the masses. Okay? That's old. That's ignoring the pulley. Okay? There's some major differences with the pulley. First of all, it's going to take longer to derive, so we may not have time for that, but let's start with our diagram. So the question below has the same picture, same setup. M1 is bigger than M2. We're going to have the same forces, but notice T1, T2. Now that you have rotation of the thing that's in between, T1 does not equal T2 or FT1, FT2. Anyone want to take a guess which rope has to have more force in order to get the job done? You could think about which tension is going to be the driver of the pulley. The one on the left, leading side, or the one on the right, the not leading side? It's actually the one on the left, okay? And so the one on the left, yes, it's pulling up on M1, so we can still keep that. M1G, still true. But that tension is now touching, it's gripping the pulley. Watch this, here's the new part. Its last point of contact is right there in purple. And so that tension force, it's still Newton's third law. It's going to be equal and opposite FT1. I'll just go with T1. Okay, it's pulling up on M1, but down on the pulley. So you still have Newton's third law, but it's not left side, right side anymore. So it's going to cause what? Rotation to the pulley. It wants to rotate in the counterclockwise direction here. As M1 goes down, the pulley rotates counterclockwise. Well, on the other side, you still have the same, M2G, but now T2 is smaller than T1. So T2 pulls up on M2, and then it also, last point of contact or first point of contact here, it's pulling down on the pulley. These two are equal. I'm going to use a double line congruency. And T2 would be trying to rotate it in the opposite direction. All right. We'll finish this one next class. We'll finish up pulleys, roll some objects, always doing net torque. Please try some equilibrium, rotational kinematics now. Don't save it for Monday night.